Hello, welcome back my fanatical physics students. This time we're going to be looking at rotational dynamics, and most specifically you're going to be looking at torque. Okay, and what is torque? Well, we've talked about spinning things, and so what causes things to spin? Well, in order for having something to spin, you have to have a force that turns something, and that's essentially what torque is. Torque is going to be any force that turns something. So look at this example of this wrench right here. So this wrench is meant to turn this nut. So the definition of torque is going to be a force perpendicular to the radius extending from the center of the turn. So if this is my radius right here, which is going to be this distance right here, any force perpendicular to that radius counts as a torque. All right, so let's just look at an example right here. What if I was to put 5 newtons of force on this? Okay, the equation for torque is torque is going to be equal force times the distance of that lever arm, or that radius from the center of the turn right here. We also call this lever arm. All right, so it's pretty simple. So what's my torque going to equal? Well, let's say that my lever arm here is 10 centimeters. So my force, which is measured in newtons, is 5 newtons. And since newtons uses meters in its measurement, we want to convert the centimeters to meters, so times 0.10 meters. So that's going to give me a total of 0.5 newtons. All right. So it's kind of a quick and easy way to look at how you figure out torque problems. Piece of cake. All you got to know is a force, and just define that force as the perpendicular force. Now, sometimes when you're dealing with this, it's not quite as simple, because what happens is you'll have a force that's going down, like we see here, but that force is not perpendicular to start with, right? So you can see that this guy, when he pushes on the pedal with his hairy foot, it creates a force, but it's in an angle. It's not quite perpendicular. So how do we do that? Well, what you're going to have to do is you're going to have to resolve the actual vector, which is perpendicular to this one. Okay, so so the vector that actually is perpendicular would be a vector that is like this right here. Okay, so let's say that to figure this out, we're going to have to know a couple things. We're going to have to know the force that's applied here on the pedal. So let's say the guy is 65 kilograms. Well, if you multiply that times 9.8, you're going to figure out his force. So that's going to give you a total of 637 newtons, right? So that means this force that is straight down is 637 newtons. Okay, so what we want, though, is we want the force perpendicular to the lever arm. So how can we figure that out? Well, we've got an angle right here. So if we go ahead and we use the same lever arm line right here, if we go ahead and draw that in here, we can make a triangle that is similar to this triangle right here, meaning that this angle is also 35 degrees right here, because these are similar angles. This being my right angle right here, and this being my right angle right here. So we can figure this out, because if I know the hypotenuse is 637, and I know that my angle theta here is 35 degrees, I can figure out this angle right here using my trig function. So SOHCAHTOA, I'm going to use the CA trig function, so the cosine of 35, which is right here. And the reason I use cos is because I want to find this adjacent angle. Here's my angle theta, so the cosine of 35 degrees equals the hypotenuse, or the adjacent, sorry. The cosine of 35 equals my adjacent, which is what we want to know here, my adjacent angle times 637 newtons, because that's my hypotenuse right here. So if I multiply the cosine of 35 times 637, I get my force as 522 newtons. And that should make sense. So 637 degrees, and I don't have it quite perpendicular, so I'm not going to get all of that 637, but my angle is not that big. It's not that far off, and so I get 522. So you can imagine that to get the full 637 newtons, you would have to be at horizontal. And as you move up, your amount of force that you can actually turn into torque, if you're pushing straight down, changes. So what you would probably do if you're riding a bike is that when the pedal is up here, you might try to push at an angle that is kind of forward a little bit. And why would you do that? Well, you would do that because you're trying to push at a perpendicular to the lever arm angle, because you intuitively would know that that's going to create the greatest torque, although you might have not known it with numbers and physics and stuff. So what is that in torque? So your actual torque then is going to be a measure of your force that is perpendicular. We figured that out by resolving this triangle. And you're going to have to multiply times the length of the lever arm. So let's say the length of this lever arm, is 18 centimeters. So we'll go times 0.81 meters. Okay. And it's something I probably should have written in here. I should have gone 18 centimeters. All right, so that would have been helpful. But anyway, so then the torque is 94 Newton meters. Okay, there's that. Let's go ahead and do one that is a little bit more challenging. Let's go ahead and look at. Well, actually, this isn't very challenging. What do you have when you have opposing torques? Well, in this situation, you have one person pushing down and giving a torque on the seesaw this way, and you have another person pushing down and giving a torque on the seesaw this way, right? And so if one person weighs a little bit more than the other, you could scoot one person in, the heavier person in, by shortening the distance. A greater force would equal then the same torque of somebody who weighs less. So let's kind of put some numbers to this and see if it makes sense to you. So let's say that this person over here weighs 43 kilograms, right? And let's say that the distance here, that their lever arm, which is the distance to the pivot point, in this is going to be 1.8 meters. Okay? Let's say that we want to know how far away this person should sit. Okay, in order for it to be perfectly even, and so they could figure this out before they even got on the seesaw. So let's say this person over here weighs 52 kilograms. Now, to figure out their force, you could multiply each of these by 9.8. But what we're doing is we're setting these opposed to each other and saying we want this torque to equal this torque. We want this torque 1 to equal torque 2. Sorry, I should have done a little squiggly line there. And so really, since these are on both sides of the equation, you don't need to include them. But I just wanted to make sure that you know that you would have to multiply by 9.8 to actually get the real force. But this is pretty simple. So if we've got 43, and 43 is times 1.8, that's going to equal 52 times something. So if you go ahead and multiply that, you're going to find out that that equals 1.5 meters. So notice that the person with the greater force will sit a little closer. And this should make sense, because if you want torque to equal torque, you're going to want the one with the greater force to have a shorter distance so that it equals one with a lesser force over a longer distance, because the two are inverse of each other. All right, so that was a pretty simple one. Let's go ahead and let's see if I can go ahead and clear that. Let's go ahead and look at a little bit more difficult one. One of these, torque equals torque with an angle measurement. So let's say that you're pressing down on a pedal, and here's your pedal right here, and so your force is going to be going straight down on this pedal right here. So that's going to be my force. Let's say you have a mass of 65 kilograms. So let's go ahead right off the bat to multiply that out times 9.8 newtons in order to find your force of gravity that's on that. So that's going to give you this 637 newtons, kind of like the last problem we did. Keep it simple. Okay, and let's say that your angle right here from vertical is 45 degrees. And so you're going to be pulling the chain in a clockwise direction. Now, with rotational dynamics, they will use the clockwise direction as negative. So I'm not quite sure why that is, but clockwise direction is the negative direction, while the counterclockwise is going to be positive. So we'll go ahead and use that in order to define our vectors. So this is going to be the positive. Sorry about the handwriting there, but you can get the idea. So what if this guy is putting a force on this pedal with his mass of 65 kilograms, what would be the force required on the chain pushing back in order for the bike to go nowhere, or in order for this to be equal. So what we want to do is another one of these torque equals torque ideas. So the force here will put a counterclockwise motion on the chain, and then the chain will pull back, or I mean, actually that's the other way around. The force here will put a clockwise force on the chain movement, and then the chain will come back with a counterclockwise movement. So let's go ahead and figure this out. So we can figure out that our force down is like this. So what we really need to know is, I'm going to go ahead and draw this over here. You could draw it on the end here if that makes more sense to you, but it'll end up giving us the same angle this way, and so it's no big deal. So here's my right angle right here, and then same as this, and so then what has happened is my 45-degree angle has transferred to right here. So here's my 45-degree angle. I know this vector here as 637 newtons, and so I want to figure out what this vector is right here. So actually, this angle right here is also going to be 45 degrees. And so I could use either one, so it doesn't really matter. Let's go ahead and just use the sine of 45. So let's go from this side right here and say the opposite over the hypotenuse. So the sine of the angle theta, so the sine of 45 is going to equal the opposite angle, which is what I want to know to figure out my force perpendicular, because remember, torque always only uses the perpendicular force. So we got to figure that out first. So this is my opposite angle. Sorry about that. That's pretty sloppy. I'm going to go ahead and redo that. My opposite angle over 637 newtons. So if I multiply the sine of 45 times 637, I'm going to get my force as 450 newtons, right? So 450 newtons is my force. Go ahead and multiply that times the distance of my lever arm. And this says my lever arm here is 17 centimeters, so I'm going to multiply that times 0.17 meters. And that is going to give me 76, I'm going to go ahead and rewrite that, 76.6 Newton meters. All right. So that's my force, or my torque, in this way. So I know that my chain going back in the opposite direction has to be 76.6 Newton meters, right? And so I don't know the force, but I do know the total distance of my sprocket. It says right here that my sprocket is 9.7, so the chain is going to be working on a distance of 9.7, so a little bit shorter distance right here. So that's going to be 0.097 meters. So go ahead and multiply that out, and I find the force needed here to be 789 newtons. So this is the force needed to counteract the force if a 65-pound person was putting their weight on a pedal which was at a 45-degree angle connected to a lever arm of 17 centimeters, which was connected to a sprocket of 9.7 centimeters, and this is how much force the chain would have to exert in order to make that thing go nowhere. So you can see that as soon as this force is greater, the chain will start to move, but only in a net force. So then you could figure out your net torque, which you could turn into a rotational motion, and we'll get into that in some of the next videos. So hopefully this helps you understand a little bit about torque and torque equaling torque.